Okay, so let me see if I can explain all of these slides to myself. So this one we didn't really go over, but hydrogenation. This was also in the textbook. Hydrogenation. I think it might have been in here actually. Whatever. I don't remember where the hydrogenation is. Oh, here we go. It's just you use like a metal catalyst, like palladium or something. That one's like not. That one's like not that important, I think. Um, this one, Binap, Carol Ligand, that gives pronounced enantioselectivity. Um, all right, here's where the real stuff gets in. So this is like acid catalyzed hydration. So you have an alkene. The double bond attacks, some hydronium ion to take a hydrogen. This forms water, but then there's a carbocation, which can undergo rearrangement. So let's say, for instance, that the H ended up here. So we had CH3, CH2, single bond CH2. The plus would be here. Well, you'd get a hydride shift to stabilize the carbocation. But then what happens to the carbocation is that another water molecule attacks, but then another water molecule steals the proton. And so you end up with an um, um, addition of water to the alkene. But the thing that I wanted to say was I don't think that there's any stereochemistry involved there because okay, so I don't think that the hydration reactions have any stereochemistry. This actually the hydrohalogenation also has no stereochemistry, but we'll see that the halogenation, where you add two halogens across the double bond, is stereoselective. Okay, give me a second. I gotta pee. And get some more coffee too. All right. Enough. Okay, so here's what happens with the hydrohalogenation. The alkene takes a proton, leaves a carbocation. Carbocation can undergo rearrangement, and then it can also attack from either side. The carbocation is going to be planar, and there's nothing inhibiting it coming from the top or the bottom. So we end up getting two pairs of enantiomers as the product. So this is going to be R. Let's see, do we have BR and H on the top? That's this one. That's going to be R as well, right? Isn't there a picture that has the... this is just halogenation. Okay, well, it's not that important. The only thing is that basically all the... So this is probably RR, SS, RS, and SR. But see here that the substituents on the two ends are not the same. So this is not meso. So there are actually 4 stereoisomers. Okay, that's fine. The product mixture contains 4 stereoisomers, 2 pairs of enantiomers. The product is optically inactive. Distillation of the final product mixture yields 2 fractions. Each fraction is optically inactive also. This rule is very interesting. Optically inactive reactants yield optically inactive products. So, that's weird. I actually don't understand that. Oh, because even in the halogenation case, it's still going to be a racemic mixture. So it's still going to be optically inactive. Okay, fair enough. All right, here we go. So this is the anti-Markovnikov hydrohalogenation. So additions to alkenes, radical additions of HX to alkenes. So hydrohalogenation. Now this apparently uses radical chemistry, so we're not really getting into it. Anti-Markovnikov products are observed when reactions are performed in the presence of peroxides such as H2O2. So here we have some alkene. It's clearly more substituted on the left. This is a tertiary carbon, and this is just a primary carbon. And we see that the Br gets added 95% of the time. I should have said to an alkene, but I think it's clear from context. Okay, but in this case, what we need to know is in this, does a carbocation form? Because I'm writing down all the mechanisms. Because it seems to me that really what you have to do is you have to memorize a couple of edges of a graph. Is that a BR plus or a BR minus? Can't even tell. Oh no, I think that's a radical. That's just a dot. Does my notes actually say that? Okay, so in the anti-Markov, did I write this down actually? Anti-Markov hydrohalogenation. No rearrangements possible. Not with the peroxide. All right, here we go. Rearrangements. So here, the alkene attacks the proton, leaves a chloride ion. And the carbocation we expect to be here on the secondary carbon. But here we have the opportunity for a tertiary. So this will methyl shift over here. Okay? And leaving the carbocation here, leaving it open for chloride's attack. And that's what happens. So the H still adds over here, but then the methyl shifts. So we end up with, yeah. It's actually cold today. Okay. So that's chill. So this is showing you a limitation of the hydrohalogenation. Okay, here we go. Now we're moving on to the second big one, which is the halogenation, which is adding two halogens. So like in this case, we have this alkene. The alkene attacks bromine gas or whatever, bromine, molecular bromine. And then the weird thing is there's an asymmetry here where we end up pushing electrons onto one of them. So this one gets no electrons and this one gets... but the important part is what forms here is not a carbocation. No carbocation forms. And the interesting thing is, because we get this bromonium ion, the electron density is higher on the top plane, or, without loss of generality, the bottom plane. And then the negative bromide ion can attack from the bottom of the top. So here, one of these is going to be like an SN2-like reaction. So if this bromide attacks, for example, the R, we end up with an S on this right here. So we get one inversion and one non-inversion, it seems. Or, well, I mean, the first one, there's no stereochemistry to begin with. So it starts off, it establishes okay, and only one pair of enantiomers form. Okay, so the main thing is that in the halogenation reaction, syn addition does not occur. Sounds good. Test? Okay. I just want to make sure. Sometimes I forget. Additions to alkenes, halogenation reactions. All right, here we go. So we're looking at the... Oh, yeah, we get an inversion. Okay. Additions to alkene halogenation reactions. I didn't really get this slide. So what's going on here is we have an alkene, we add molecular bromine, we form the bromonium ion. I don't really know what this slide is talking about. Another picture of the mechanism. Here's the interesting thing is what side? What side? Wait, actually, I don't think I'm right in saying that no carbocation forms, because it looks like a carbocation does form. Okay, so it's not. Yeah, okay. Okay, this one's interesting. I had to write this mechanism out. So, um, alkene addition, halogenation on a ring, where the alkene is on a ring. So, let's imagine that the bromonium ion attacks, or that the alkene attacks the molecular bromine on the bottom side. The bromonium forms on the bottom, and let's say the hydrogens, the other two substituents of the alkene, are pointing up. Well, now imagine that the bromide ion attacks from the top, here, specifically here. It's different if it attacks from here. Well, then this goes pushed onto the bromide, so then this is going to be pointing down, and this is going to be pointing up. Then similarly, this is going to be pointing down, and this is going to be pointing up. However, you have to see that by inverting this is going to be axially down, and this is going to be axially up, meaning that both of the bromines are going to be equatorial. And that's a gauche interaction, and that's not good. It's not anti. Oh, and the ring is locked. There's no way to ring flip this. This stereoisomer is not observed. The bromines have not kept anti to each other, but have become gauche as displacement proceeds. So here's the correct one. The bromine adds to the other side here. This is right now a very weird configuration, but it's this is going to invert. So this is up. This is going to go. So, well, this is already, I guess, axially down. Equatorial up. This goes axially down. BR becomes equatorially up. Or axially up. So we get the anti. All right, sounds good. Antara facial? What does that mean? Whoa. Okay, wait. So what do I expect to happen here? I'm not even looking at the products. We expect an anti. Why is this minor, though? All right, we're going to have to draw some chairs. So the 4 down, down. This is the main product. And this is up. Uh, yeah, no, yeah. This is the major product, and this is the minor product. But why? So we have this T-butyl, right? That's what that is. Oh, so I guess one thing is like when we started off with the ene, presumably we were able to force the ene so that this has to be equatorial. I mean, just because the steric hindrance of it, with the 1,3 diaxial interactions when it's axial. So this has to be equatorial. So let's start to draw this. Antara facial. Okay, so let's put this here. So this is going to be okay, the ene is here. This is going to be T-butoxide. Not butoxide, but T-butane. I don't know what you T-butyl. That's what you say. When it's an alkyl group, you say T-butyl group. Okay? And what we want to do is we have Br bonded to Br. And the ene attacks. And so let's just say that this is okay, let's just say this is equatorial down. This is equatorial down. This is H. So this is T-bu. This is H. Axially up, so axially down. So, and now here, does a bromonium ion form? It must, right? So let's just say that it added down. I don't think it matters. Actually, I want a new one. Let's try to read this, but this is like crazy. Antarafacial and suprafacial are two topological concepts describing the relationship between two simultaneous chemical bond making and or breaking processes in or around a reaction center. The reaction center can be a p or spn orbital, a conjugated system, pi, or even a sigma bond. So I think first off we're talking about this. The relationship is antarafacial when opposite faces of the pi system or isolated orbital are involved in the process. I mean, for real, what the heck are they talking about? I don't know what that is. The alkene first forms a bromonium ion, not a free carbocation. Then Br minus attacks the opposite face. We know that. So overall, two Br atoms end up anti to each other. The tert butyl strongly prefers equatorial. A Tbu is so bulky that it basically locks the cyclohexane chair in the conformation where Tbu is equatorial. So we kind of got that. So attack is less hindered. Is attack from the less hindered face is favored. If Br2 if Br2 approaches from the face closer to the T-butyl group, I think this should be here, right? Okay, so now we need low key. That's like I'm gonna put a pin in that. I'm gonna put a pin in this thing. I don't get it. All right, here we go. Epoxidation. Okay, so this is important. S3-methylcyclohexonine. So uh wait, I'm so confused. This thing is the same as this thing. This thing is the same as this thing. Why are they crossing them out? Oh no, more of this. Okay, all the interfacial stuff I'm not getting. All right, here we go. Um, all right, we're looking back again at halohydration. Wait, halohydration reactions. What is that? What the freak? Let's see, is halohydration in here? Halohydrins? I think that's this. Halohydration. Wait, is it halohydration or? Yeah, halohydration. So I think it is halohydrin. So in this case, halo alcohol or a halohydrin. It's also adding XOH anti. So it's like a the arrow is like a Br2 in water or something like that. So in all of these things, they're kind of just telling you, here's something that could happen. They don't tell you how much, but they tell you, hey, like this could happen. Non-reacting fragment unchanged. We have regioselectivity, meaning that it's more likely that the OH or the Cl is going to add here. What is the major product? The OH adds there. And why is that? That's kind of interesting. Why is that? Let me get some pants. Okay. What do they call helonium ion? Wait, actually, hold on. I gotta do something. Okay. Okay. Halohydration or halohydration. Halohydration. Okay, I mean it's actually pretty easy. This I don't know about though. This 2-butene. I don't know what this slide is even telling me. Okay, here we go. Now we get to the oxymercuration. Okay, so yes, the question is, for these pathways, what does it do? Okay, it adds an alcohol group onto, and then what is the regioselectivity? It's Markovnikov. And the main thing here is that in our typical, so when we went back to how to add an alcohol, what we could have done is, so, oh yeah, I literally just drew this. This is exactly what I just drew. Okay, cool. Yeah, so I just drew this, and they're saying if you do this in acid, just normally, you're gonna get a rearrangement. But here, so the main advantage of the oxymercuration is that we get a so this is gonna be HgOAC2. That's the first thing. Then the second thing is sodium borohydride. And I don't think we need to know the mechanism by which the borohydride takes off. I think all we have to do is know that this combination of reagents and environment condition or whatever, reaction condition leads to the Markovnikov addition of an alcohol without rearrangement. Which is pretty cool. I mean, that's pretty sweet. Oh, here we go. Here's a good picture, though. Mercurinium. So I guess there is still a question, though. It's yeah, it adds on the more substituted side. So that's how we get the Markovnikov product. And let's see, how does this work? I don't know. I guess they don't care how that works. I think it's like beyond the scope. I think that's why they don't show it. Okay, hydroboration. Hydroboration, I think, is also adding alcohol. So this is. Interesting. SN2. Yeah, okay. Let's look at the toxicity of this stuff. Okay. We just need anhydrous tetrahydrofuran. No, I think you want this. That's pretty expensive. That's pretty expensive. Um, epoxy butane. 1, 2, 3, 4. That's weird. I've never seen that before. So, okay, so how do I make one pentene? The easiest textbook route is dehydrohalogenation. Dehydrohalogenation. Okay, so we were just learning about hydrohalogenation. So now we're doing dehydro of one halopentane. Okay, interesting. Start from one bromopentane or one chloropentane. So let's see, like, how much does that cost, for example? Can you just buy that? Okay, one bromopentane. Or can I? Okay, well, whatever. Let's see, what's the cost of that? Okay, so interestingly, but it's got to be water. Maybe, is it water soluble? Okay, but it's cheap. This stuff is really cheap. How do they make that though? I mean, presumably that's cheap. I don't know. Is it? I don't know if 100 grams is a lot. Do they not sell it as a liquid? Bro, come on. Okay, that's good enough for me. Okay. Um. Okay, hydroboration. Hydroboration is also adding OH, but it's syn and anti-Markovnikov. So that's pretty cool. What if 3 cyno 1 phenylpropone reaction with excess methyl? Bro, this guy wants a shout out. Kabir Patel wants a shout out. And then hydrolysis. Dude, I don't know that. This is freaking intro organic chemistry. Okay, so let's start to get this down though. So I think it's a matter of memorizing this. Two, three, four, five, six. Okay, one. This is one hexene. And here are the reagents. We add BH3, and then we add a peroxide H2O2 and a strong base NaOH. And then we get, 2, 3, 4, 5, 6 OH. So wait, but where's, oh, here we go. We need a picture of the syn. Yeah, okay, so syn addition. Okay, so let's do this. Okay, so we don't have really a picture of the reaction mechanism. But let's Okay, hydration reaction. All right, so let's just draw this out. So we're gonna get, let's say, oh, and what we need to know though is that it's anti-Markovnikov. So that means the OH is gonna go here. Okay, that seems good to me. Syn, anti-Markovnikov, hydration reaction. That's hydroboration. All right. Um, additions to alkenes, hydroboration reactions. Uh, okay, so I'm not getting the mechanism of the hydroboration, but all right, give a synthesis of 2-hexanol from any alkene. All right, you just add acid to you definitely don't want to do this one. You want to use this one. The reason why you want to use this one is because here, if it's on the end, then this is a secondary carbon and this is a primary carbon. And so the acid catalyzed hydration will be Markovnikov. So you just add acid to this thing and it's done. It says use mercuration reduction, but in this case, I feel like there's no reason why you actually need to do that. Additions to alkenes. Oh wait, I need to know this one. This is for the diol. Um Oh yeah, we need to know this. I forgot. There's actually a lot of these to remember. Okay, so the seventh one is osmium tetroxide. I think there's probably peroxy acid. Oh yeah, ozonolysis, ozone. The ozonolysis is oh yeah, the carbene. Okay, so that's it. So let's go back to the osmium tetroxide thing. So this is OSO4. And let's just say we have an alkene. So pentene or cyclopentene. Um, so wait, actually what we want to do is we want to write 1 OSO4 osmium tetroxide, then sodium bisulfite. Sodium bisulfite. So NaSO3H, sodium bisulfite. Yeah. NaHSO3 and in water. And so what that's going to give us is a cis diol. Okay, so it's a syn addition. So a cis diol. So we're going to get OH and OH. And oh, also, okay, yeah, also, so this is the eighth mechanism. What is it? Cold, dilute, slightly alkaline. Potassium permanganate. KMNO4 does the same. Okay. I honestly might even make like flashcards for this because it's like so. I feel like some of these are just niche. I think the important thing is probably remember that what we're interested in is finding ways to manipulate alkenes. And here is like a list of weird things that you can do to alkenes. And so, let's just go through the whole list of things that we can do to alkenes. So the first thing we can do is hydration reactions. And the easiest thing to do that is just to add an acid, and that will give you an alcohol group. So hydration means adding H and OH onto the sides of the but in this case, let's see, a carbocation forms. So we add an acid, we have to be sure that nothing funky happens. But okay, the simplest way to hydrate an alkene is to add acid. The second thing we can do to the alkene is hydrohalogenation. Wait. There's hydrohalogenation, but then there's also hydrohalogenation and halohydration are two separate things. Halohydrogenation is different from hydrohalogenation. One adds HX, the other HOX. Hydrohalogenation means adding HX across a double bond. Halohydrogenation halohydrin. Okay, that's going to be interesting to try to remember because those are very similar names. Okay, then the next thing that we can do is we can just do halogenation, which is adding two halogens across the double bond. And this one is stereorestrictive. There's only certain stereochemistry that comes with that one. And it has to be an anti-addition. Okay. All right. Number 4 is halohydration, which is forming a halohydrin. I think that's in here, right? Halohydrin. Okay, that's good. Okay, then oxymercuration, hydroboration, osmium tetroxide, and potassium permanganate. Okay. I am interested in the epoxidation reactions. We need to do this. So using a peroxy acid, isn't there that weird one like Okay, so I was right that this is the MCBPA thing. Right, so we have some alkene here. We add this peracid. And we get an epoxide. And then we add acid. The acid, the oxygen attacks the acid. We get a oxonium ion. Okay, then water. And water does like an SN2 to break open the ring. So here we can make a di. Is diol specifically for vicinal? I'm pretty sure that diol just means any compound with two hydroxyl groups. Yeah. The protonated epoxide is analogous to the cyclic bromonium ion. So this has got to be anti. So I don't know. Some stereochemistry is involved here. That's pretty interesting. Okay, ozonolysis. This one was the most confusing one to me. I had no idea what he was doing. I mean, like, I get this. This is not that bad. Or was it this one? There was one where it was talking about the reduction of the molecule. Oh, this is actually so sick. All right, so let's do this. Ozonolysis. What's the second reagent? What do you call that? You call that a thioester or something? Dimethyl thioester or something? Dimethyl sulfide. Oh, okay, that's an easier name. I don't know why I was trying to like do something crazy. Okay, anyways, so we dimethyl sulfide. And this forms uh two carbonyls. Reaction can be used to break larger molecules down into smaller parts. 2-butene. I don't get this slide. This slide's weird. All right, I think we should start doing the problems. Okay, so acid and water. Okay, so the first thing we gotta see is, I'm guessing, okay, so the carbocation clearly forms here. Okay, so first off, what is the mechanism? The mechanism is acid catalyzed hydration, right? Acid catalyzed hydration. And what's going to form is, now we're going to get H2O comes and attacks the tertiary carbocation, which is going to form I think that they're just trying to make it look complicated, but I think it's not that complicated. Yeah, that's what I said. Yeah, I should have said Markovnikov, but I think I was right. Okay, second one. Okay, acid. Oh man, I'm gonna have to get good at drawing, huh? Okay. All right, so acid and water. So, we need to provide the mechanism that uh wait, what? I don't understand how you open up. So wait, first off, like what it looks like to me is this is 1,4. So if you were to leave this, if you were to leave this alkene, break this bond, then you'd have like a, but I don't get it. You get an 8OH here with the acid. Try to draw this thing. All right, so we're gonna get a ring, and then we're gonna get a thing like this. Bro. Oh, I hate. Wait, is that actually? Why is this so bad? Okay. So there we go. So we have the ring, and now what we need is, uh, so across from this, we want a methyl, and then on that here we want a double bond. Okay, so that looks like the structure to me. So okay, wait. So we found the compound for this. Now let's draw the two products. I wish there was like tabs. We gotta make a. If I change it on one tab, is it gonna change it on the other? I just don't understand how this is possible. All right, let's try to do this thing now. Um, just delete it. So now we're trying to make. We got a ring. Okay, skipping two. Two makes no sense to me. Wait, here we go. We have a peroxy acid. And what does the peroxy acid do? It uh the peroxy acid one, fuck, I don't remember. I have no idea. What does it do? Oh, it forms an epoxide. Dude, what? Okay, wait, here's what's gonna happen. So this thing is gonna form this ring. What's the mechanism of the epoxide? We have acid? We don't really have acid, do we? Oh, wait, actually, you know, I want to do this. All right, let's just run through the gamut. If we add an acid, maybe it'll promote this leaving group. And then you have a carbocation there. And you just get SN1 substitution. That's not going to be what you want. Maybe you can give 2 steps. Because what we are doing here is we're doing the hydrohalogenation of... Well, but there's no alkene, so it's not really what we're doing. But we're adding an... Well, okay, the first thing is, how do we make an alkene from an alcohol? Well, we want to add a strong base. So let's say we added a strong base to this thing. If we added like NaOH... Okay, actually, yeah, if we add NaOH, Then we have an H here and an H here. The OH comes in, grabs this proton. This forms an alkene, kicks off the other OH. So step one is add NaOH. Then we have an alkene. Okay. Once we have the alkene, we just need to do anti-Markovnikov halo hydrohalogenation. Halohydrin is the wrong one. Hydrohalogenation. That's what we're trying to do. We're trying to do anti-Markovnikov hydrohalogenation, which is we're trying to add HBr, HX. Oh yeah, that's right. You can do it. So what we're gonna do is we're gonna add HBr in peroxide. Okay, so this first one. First, add NaOH. The strong base will undergo E2 elimination and kick off the OH group. The side the double bond forms on doesn't matter because the rest is equivalent. The rest of the molecule is symmetric. So that's A. B. Add HBr in H2O2 ROOR. This gives the anti-Markovnikov product. Anti-Markovnikov hydro Ooh, these problems are actually kind of fun. I'm actually liking it now. I was feeling so lost. Okay, good. So that one, I think I got it. I mean, what else could you do? You have to form an alkene first. I think that's the trick. Okay, here we go. This one looks really easy. Is it? Yeah, this one's easy. This is just going to be add acid. This is just going to be add, H2SO4 or something. We are hydrating an alkene and putting the OH group on the more substituted carbon. So adding acid will do this. Because if we, let's just work it out. So we have That one was quite simple. Okay, here we're also doing a syn a syn hydration across the alkene. Um can you put wedges and dashes in this thing? No. Well, first off, the other thing to note is this is anti-Markovnikov. Um, is it hydroboration? Does hydroboration? I thought hydroboration did an anti-addition. No, it's hydroboration. So then why does Right. But this is kind of a different thing. But here, these are kind of the this and this are kind of the interesting ones. So in a way, you can think of this as Markovnikov, but this is actually a better way to put it: is that the OH specifically is on the more substituted, because the thing that forms the halonium ion is obviously the halogen. The OH can't do that. So Sin Markovnikov, we don't have one for Sin Markovnikov. Or well, but we have one for. So this is going to be the H3O plus. Anti-addition, do we have that for OH? Not exactly. Huh. Okay, let's keep going. I think that was actually really helpful. So what we're going to have to do here is we're going to have to add BH3. What is the second one? Like, I'm going to need to make some flashcards to remember these reagents. Peroxide and base. I'm going to make some food.